Thank you very much, Gwendolyn. It's a pleasure to be here. It's a great opportunity to come back and talk with our friends at IFPRI, and particularly about the role science can play in dealing with the challenges that are going to be confronting us, particularly in the context of climate change. And I'm going to limit my remarks to just a few examples of what we're talking about. But just want to remind you that I am Director General of the International Rice Research Institute. We've been around since 1960. We were founded in an atmosphere of grave concern over global food security by the Ford and Rockefeller Foundations. We were tasked with a very straightforward mission. It was basically one that addressed hunger and poverty, looking at the maintaining or improving the health of rice farmers and consumers, and realizing that two very important dimensions. First, that any agricultural innovation, particularly in the area of rice, will have to be sustainable. That is, the rice paddies that are feeding today's populations will have to be feeding populations for generations to come. So whatever we do has to be sustainable. And the second was that we must work in partnerships. Any institution of any size to have an impact globally has to be very clear about its partners. And I think it's good to remind people who aren't intimately associated with the world of rice, really where rice sits in the world. It is perhaps the oldest domesticated crop, 10 to 14,000 years ago, various estimates. It is tremendously diverse genetically. I'll talk about the implications of that in a minute or two. Domestication, in fact, may still be going on in the Asian rice paddies, unlike our other major staples. But it is more than just a food. It is, of course, the primary food for the world's poor, feeds about half the world's population overall. But in the vast majority of rice-growing countries, particularly in Asia, rice is much more than a food. It occupies a central part of the culture, the social identity of people. So if you're talking about any impact of rice supply, particularly or price in Asia, you talk about an existential crisis for the population. I used to wave my arms about this, but a paper came out in Science last May, and I refer all of you to it, where they did a careful analysis of the cultural values of societies that grew up around rice cultivation compared to wheat, and they found that there were very significant differences in terms of about how communities were structured and organized and their value systems. And I refer you to that. It's really quite a good read. Very equally important, rice flourishes in a monsoonal environment. Those environments that will wipe out just about any other major staple crop is a very happy environment for rice. It's very happy growing up to its knees in rice or in water, unlike any other staple. It's also grown by very small farmers. A typical rice farm is less than a couple of hectares. It's their own seed. Still today, a heavy reliance on human labor or, at the very best, small machinery. A question we have to address is how long is that going to be tenable? I would argue that not very much longer. And that has major implications on investments in rice research and development and overall strategic planning at national levels. We probably won't have time to get into in this presentation. If we look at rice consumption, the darker colors indicate greater consumption. What's striking is that rice is becoming more and more important in sub-Saharan Africa. In fact, in sub-Saharan Africa, the consumption of rice is growing faster than anywhere else in the world and faster than any other commodity in sub-Saharan Africa. I expect in the next 10 to 20 years, rice will be the primary staple in most sub-Saharan Africa countries. When we overlay poverty, we can see that the largest concentrations of poverty coincide with rice eating areas. So if you want to do something about poverty, rice will have to be a part of that equation. And we expect the demand to continue to grow. The next couple of decades, another 120 million hectares of tons of rice, million tons of rice will be needed to meet global demand. So we don't see anything other than additional challenges for rice supplies. Climate change will have a major impact on rice production. Temperature, rainfall, sea level rise, and weather hazards will all be a serious problem. And if we consider that most rice is grown, or a large amount of the world's rice is grown at river deltas, and river deltas are by definition at sea level, there are going to be major challenges to rice supplies coming out of those areas. So where is the rice going to come from that we need? It's going to come from increasing productivity on existing areas. I don't think we want to be clearing very vast areas for rice production. We're having major stress put on our rice production areas, and that land is moving out of agriculture in general and out of rice in particular. Labor being attracted to much less arduous ways to make a living, and water diverted to industrial and urban uses. So the rice that we produce in the future is going to have to be grown under these kinds of constraints. And so we are faced with having to increase productivity, but in ways that challenge us in terms of changing how rice is grown. I think that's a major both opportunity and challenge that face us. And we're going to have to increase our productivity just to stay where we are. And that's not good enough in my opinion. And I do want to remind folks that if Asia is food insecure, then the world is, or if Asia is rice insecure, then the world is food insecure. So we'll need a second green revolution, but it's got to be very much science-based. And when I say science-based, it means that we take advantage of these tremendous revolutions in genetics, molecular biology, physiology. We have the chance now, like ever before, to understand what's happening in the soil of the rice paddy, to better understand how to manage rice nutrition. We have a revolution in both computational power and communications technology, all of which allow us to address problems at scales of complexity that were not really imagined 10 or 15 years ago. So we have the foundation for a dramatic revolution in our understanding and development of technologies around our major staple crops. And I would like to think that we have a better understanding in the research community about how important it is to engage the political agenda, policymakers and decision makers, and I think that Schengen will be talking about that. But without that final point, all the great work we do will amount to not very much. So a couple of words on the genetic diversity within rice. There are over almost now 120,000 different rice varieties in our gene bank at IRRI. The genetic diversity of that is just astounding. We include wild relatives as well. Very few have been used really in breeding programs until now, but just recently we completed the sequencing of 3,000 lines out of our gene bank. Remind you that in 2005, the cover page of Science magazine had a big, beautiful picture of rice terraces celebrating the sequencing of the first rice genome. And now we've done, 10 years later, 3,000. So it's a tremendous accomplishment. And that will enable us to produce rices that are climate ready, rices that are drought tolerant, flood tolerant, heat tolerant, etc. And I want to say, just give an example of the application of flood tolerant rice. Rice likes to grow in water that's 10, 15, 20, 30 centimeters deep. If it goes completely underwater in a flood, it will drown like any other plant. And those kinds of floods happen throughout Asia and in the inland valleys of sub-Saharan Africa on a regular basis. Even favorable areas get some kind of flooding. So every year we suffer significant losses to floods. Now our scientists in our gene bank did identify flood-tolerant rice, but it was devilishly difficult to get it into a genetic background that farmers would grow. Using the tools of molecular biology, we were able to achieve flood-tolerant rice in a high-yielding background with good grain quality. some of the older varieties were so bad that farmers told us who sampled them that they wouldn't even feed it to their dog. So you have to pay attention to, if you can't even produce dog food, you got a problem. Well, we developed, our scientists, after a major effort, developed a flood-tolerant rice, and I love this slide because it shows the varieties in the white lettering that do not have the flood-tolerant gene in it, called sub-1, submergence 1, compared to the same varieties in yellow lettering that do have the flood-tolerant gene in it. And the reason I really like this slide is that it shows that I really didn't need to spend so much work on statistics at university, because you can tell pretty well the difference without doing any statistical analysis. But this field was under water, completely underwater for over 2 weeks. Imagine a flood. Imagine yourself living in a village and your rice field is completely flooded. You're on in a canoe for 2 weeks and it recedes and you can still get a crop from that field. It is a phenomenal achievement. But we took it out to farmers' fields. This is taken on July 31st, 2008. Mr. Paul's field. His field had been subject to 2 floods, and we had him plant, at the beginning of the season, flood-tolerant rice. This is what it looked like after the second flood water receded. And his neighbors were laughing and telling him, plow it up. And we said, no, please wait. This will come back after. And so he didn't plow it up. And that's what that same field looked like on October 31st. And it's a spectacular, they call it miraculous, the farmers, to put it, there's no other word for it. And with support from USAID, Gates Foundation, Government of India, Japan, we've been distributing these materials. And on end of 2013, 4 million farmers have already received seed of this material. So it's moving out very, very well. And I would like to go out on a limb, and I state publicly now that the second green revolution that we say we need actually started at 1:18 in the afternoon on July 31st, 2008, when Mr. Paul did not plow up his field. And that is the mark of the new generation of scientific advances that are making it to farmers' fields. And this is really mind-blowing to me. Research team out of Berkeley, Alain Janvry's group, came out and had a look at these materials in farmers' field to say, is this stuff really any good? And they went out and they published one of Nature's journals, a paper in which they describe the work, and their concluding statement is that this study indicates that scheduled casts are likely to be a major beneficiary from the spread of Swarna sub-1 in India. I mean, that's an earth-shaking statement, that the lowest of the low, the people at the bottom of the heap, are going to be the ones who differentially benefit. Think about the original criticisms, legitimate criticisms of the Green Revolution. The first one, lift the marginal people behind. Well, and that's because it was really hard. Well, we're addressing those issues front and center now. What's really cool is that we're able to combine drought tolerance, which I won't talk about because it's a long story as well, with submergence tolerance in the same variety. Farmers in these areas can suffer a drought early in the season and then a flood, or vice versa. So really, to make a big difference, you need to have tolerance to both. And we've succeeded in that. And the reason is that the mechanisms that confer drought tolerance and submergence tolerance are completely different. Now, managing the crop, an equally significant problem. What is the most efficient way to manage your crop, particularly as your management conditions change, your labor circumstances change, etc. So I just want to give you a quick example on nutrient management. We have, over the last couple of decades, been collecting detailed assessments of farmer fertilizer use across South and Southeast Asia, and doing on-farm experiments in terms of nutrient manipulation, and have come up with very, very sophisticated databases and models linked to our crop growth models that tell us how to come at the best recommendation for a farmer in the farmer's field, given their particular circumstances. So we put together lots of tools that were available for farmers, and farmers didn't use them because they were actually too complicated, etc. Finally came to us that we needed to be looking at cell phone technology, etc. no big surprise. Farmers understand how to use a cell phone. And we've been able to link our crop growth models with our knowledge of local conditions and practices, so that farmers, or probably more likely crop advisors, will be able to derive field-specific recommendations. Very simple questions. What variety are you expecting to grow? What did you do with your residue from your previous crop? What was your previous crop? What is the source of your irrigation water? All of those, you put that information together with the site-specific knowledge that you have by your geo-positioning on your cell phone, and you can give a farmer very specific recommendations on fertilizer use. And we see this growing. We're already linking this with recommendations on crop protection, looking at water management. All of these we can put together in a platform that will provide those who are the farmers or those who are advising farmers with decision-making tools that are relevant to the specifics of their field. Previously, we had blanket recommendations. Now we're able to get very specific. And I think we're really at the edge of transforming the way farmers receive and manage advice regarding their crops. And I think I expect that there won't be farmers, individual farmers, going and seeking the information. I expect we'll see the growth of small entrepreneurial ag service advisors in many areas. So finally, just to close, and a link to a little bit what Shengen will be talking about, and Rob, I hope, is that what do we need to be able to make long-term decisions in planning at the policy level? We need very good information about crop yields, crop production, and we need that in real time. We don't have that. Our sources of data are very, very poor. What is the harvested area in a country? When will it be harvested? What is the expected yield? You try to find that information out in real time. You go to FAO books, and they're 2 years out of date, or you go to USDA, and they're basically based on somebody calling up the USDA officer in each embassy, and yeah, the minister says we're going to be getting this much, boom. Okay, so the data really aren't very good. But we've been working on a combination of technologies that allow us to use remote sensing technology to map out what's happening in real time. And what we've been using, in fact, are radar satellite imagery from microwave generating satellites rather than the optical. The problem with the optical satellite imagery is that during the monsoon season, when half the rice in the world are grown, or more than half the rice is grown, when you take pictures, you get pictures of clouds. And that really doesn't help you anything. But the radar imagery is generated from microwaves that penetrate clouds. You can distinguish. We've got some really great algorithms worked on with a company in Switzerland that uses these satellites for land use modeling. To distinguish rice paddy, water, bare earth, forest signals, so we could actually get down and get a less than just a few square meter resolution of what is rice and what is not rice, and better yet, when it's planted. And just as an example here, the Mekong, this is a couple years ago, we were ground truthing this methodology, where these are yield estimates. Based on this satellite imagery. And what happens is we are able to identify when the crop was planted in each parcel, and connecting that planting date with our plant growth models, because planting date is one of the most important determinants of yield. Adjusting it through the season based on weather data, we can get very good estimates of the productivity expected from each field. And putting that together, you start to come up with some very, very sophisticated, accurate estimates of production. And we're ground truthing this, and the yield estimates are now at over 85% accurate compared to crop cutting. So we're making a lot of progress. And what we expect is that we will have real-time estimates of the major rice growing area production in just a couple of years. And of course, this allows us to go through a whole suite of let me see, where are we? I can't quite read that. Oh, amazing. The tool that this tool is great for policymakers in terms of regional applications, but also local applications in terms of what's happening with diseases, what's happening with pests, etc. And putting together and working with IFPRI on this, we see that there's a great opportunity to build very sophisticated information gateways around rice. You know, what's going on at the regional level, what's going on at the local level, linking this with our knowledge of trade and production, and starting to come up with much richer, much more detailed, much more sophisticated estimates for policymakers. So I think it's clear that the next green revolution is underway. We have a new suite of technologies that will transform what's happening in the rice field. I hope it will transform what's happening in rice trade, because that's, as Shengen knows, is a mess. We have a great demand for the technologies at various levels. You know, the farm level, certainly the private sector is increasingly interested, and policymakers are also very, very interested. So with that, I just would like to remind you that the precious things in life are not just pearls and jade, but the 5 grains, and rice is, of course, the finest. So with that, thank you very much.